Okay, guys, because I'm not here on Monday, um, and I don't have access to my document camera at home, I'm going to go old school, as if 1 year of taking physics can actually be called old school, and we're going to do it back on the dossier. Um, we started with circuit symbols in our discussion of capacitors, and so I want to do a quick review that we had. We had a long and a short, and this was this is a battery. Okay, and with the battery, the long end is the positive end, and the short end is the negative end, and that'll actually make a difference when we start doing some circuit analysis, and we'll get more into that later. And we have a capacitor, which looks a lot like a battery, except both lengths are the same, and we have a switch. So that's a capacitor, and then we have a switch, which is looks like that, and this opens and closes the circuit. So it's a switch. All right, and so we can put these together in a circuit where we start with a battery. And we'll put our switch in here. All right, and when we go around, and we'll say like this is a car battery, and a standard car battery is 12 volts. 12 volts, and so whenever we go across, we go for a walk. This is our voltage walk. So if we go across, okay, we're going around our we go around our circuit here. Whenever we go across right here, okay, we have a change in voltage. And so if we go, if we go from negative to positive, all of a sudden we increase our potential by 12 volts. And then we go around, and by the time we get over to the other side, we have to be at 0 volts. Down here. And so what takes all of this potential is our capacitor, which is right here. And this uses the potential it uses the potential, and it acquires as much charge on this part of the battery as is possible. And it acquires as much charge on this battery as possible to give us a 12 volt potential across our capacitor. Okay, and those charges just sit there. The charges sit there on the capacitor until the electrostatic conditions are such that the charge will actually jump down the capacitor, and the voltage, and the voltage decreases. So then all of a sudden on the other side, our voltage down here will equal 0 over on the other side, where our voltage over above the capacitor equaled 12 volts on top. And I apologize for my messy handwriting. Okay, so then it goes around the switch, and then as as a voltage man, you know, trying to remember how to get the pointer back out. I don't remember how to do that. How do I get the pointer out? Anyways, so voltage man walks across, okay, and he goes for his voltage walk, and as he comes back up to the potential, it's like riding the chain on the roller coaster. He goes back up and he gains his potential again, and he comes back around, and the capacitor is the drop that he goes down, so he loses all this potential. Okay. And when you end up when you go through a circuit, when you end up where you start, the total change in voltage is 0. So let's say we have this place up here. This place right here is where we're starting. As we go down, okay, well, we're going to have a voltage drop. We're going to have like negative 12 volts. And then we're going to come around to the other side. And, oh, here's something that's going to add 12 volts. And we get back to here. And so our change in voltage as we go around is 0 from any particular point on the loop. Okay, in fact, that's called the loop rule. That as you go around a loop, the total change in voltage equals 0. So let's take a look at our capacitor even more closely. And let's start our capacitor here. Let's get really big with our capacitor. And on one side, we're going to get all of our positive charge. And on the other side, we're going to have our negative. And across the capacitors must be electrically neutral, because the amount of charge that you're gaining on one side of the circuit has to come from the other side of the circuit. And so I wish I could remember how to do that. Okay, we figured it out. Here's my pointer. So the charge that we get across here has to equal the charge that we have down here, because if you look at our circuit up here, that if we're going to accumulate, if this is going to force positive charges up and around and accumulate them down here, they have to come from somewhere, and that creates a negative down here. That's kind of like all the positive gets sucked around this way. Now, we all know that in real life it's electrons that are getting forced the other direction, but that's not how we study circuits, and so get past the idea of a flow of electrons. Think of it as flow of positive charge. Everything is flow of positive charge that we're dealing with. All right. Now, if our voltage equals negative integral. Let me just go back and do this. If our voltage equals negative integral E dot ds. All right. And since E dot ds is positive, if we're always going in this direction, right? That's our field. And if we're a little test charge, I'm a little test charge short and stout. If I'm a little test charge right here, okay, then I'm going to want to move that way. Okay. And so if our change in voltage is positive, then if our E dot ds is positive, right, if our field times the direction of the field is positive, then our voltage is going to be negative, okay, which should make sense here. And so our capacity here, our capacitance, okay, equals Q, the amount of charge on one of these, divided by the voltage. Okay, so this is one capacitor. Now, if we go to a new one, okay, and so now we're going to talk about parallel capacitors. And so we're going to draw a new circuit, and we're going to have, in fact, we're going to do a double battery here. And each time you have one of these cells, it's adding a little bit of voltage. So let's say each one of these was, this total thing is going to be 12. Each one of these is going to be 6, so we'll have a total of 12 volts again, equals our delta V, equals our delta V. Alright, we go back around, except this time, we have a capacitor here, and we're going to have a capacitor over here, which means you have a choice that you can either go, okay, so right here, right at that point right there, you have a choice. You can either go through this capacitor, or you can go through this capacitor. Okay, and that creates two different loops. So we have a loop here, or we have an outer loop that goes like that. Either way, what our rule is, every time you start and you return to the same point in a loop, our total potential equals 0. Okay, and capacitors, the term for this is capacitors. Capacitors are in parallel if they have the same voltage drop. All right, they are in parallel if they have the same voltage drop. So, or in other words, delta V1 equals delta V2. All right, so if we go through the red loop here, okay, if we go through the red loop, then we would have this capacitance in C1. All right, we have to get really small here. C1 is going to equal Q1 over delta V1. Okay, and then over here we're going to have the same idea. We're going to have C2 equals Q2 over delta V2 for this loop on the other side. And let's say there's less charge on it. There's only 3 pluses and 3 minuses. Okay. So the total charge that this battery is forcing onto these capacitors is going to be Q1 plus Q2. All right, so we have the total charge. The total charge equals Q1 plus Q2, and we will call this Q. Okay, we'll call that the total charge. Q equals Q1 plus Q2. All right, well, if our capacitor, if C1, okay, is Q1 over V, okay, because because we know V1 equals V2, so our second capacitor equals Q2 over V. Then our total capacitance equals C1 plus C2 is going to equal Q1 plus Q2 over V if we add those fractions together. Alright, well, that should make sense. Okay, so let's multiply the V over, and so if we have our total capacitance times V is going to equal our charge, which equals C1 delta V1 plus C2 delta V2. And I wish the writing could be neater. Let me see if I can do that again. Let's see if I can just be more clear with this. We get C1 delta V1 plus C2 delta V2, right? Or, in parallel, our total capacitor equals C1 plus C2 plus C to the N. Okay. And this gives us the equivalent capacitance. The equivalent capacitance of the circuit. Okay, so what is the total capacitance on the circuit? You add all the capacitors in parallel, and you get this. You add all of them up there in parallel, and you get this. You get this value for your total capacitance of the circuit. Okay, so that's for parallel capacitors. Then we have capacitors in series. Okay, so now we have capacitors in series. And yes, I know that the writing is terrible. In fact, this over here should have been, if I'm going to give this a title down here in the corner, this is parallel. Parallel, oh God, that's horrible. Let me try it a different way. Let's try that is moderately better. Okay, parallel capacitors. Okay, so over here we have capacitors in series. And let's go over these. Alright, so now we have a new circuit. And now, instead of being two different loops, we now have the same loop. But this is going to be really cool. Alright, so here's our circuit, and once again we're going to have a 12-volt battery. Okay, now this 12-volt battery, because this is a circuit, is going to pull charge in that direction. It's going to pull here, it's going to drag it around, okay, and it's going to put positive charges It's going to put these positive charges down here on the top of this one. Okay, and it's going to create, well, here's the thing, where did it get where did it get those positive charges? Because right in here, there are breaks in the circuit, right? It's not allowing charge to flow. Charge does not flow through these capacitors. Okay, so these positives over here have to come from the other end of the circuit, which is this area down here. And so that means we get a negative on this end of the other capacitor because it's not allowing charge to flow. So we get this net negative charge on the back end and a net positive charge on the front end. Okay, but this positive over here, this positive is going to create an imbalance over here. This positive is going to start attracting negative charges to it on the other side of the capacitor. And these negatives are going to start attracting positive charges on this side. And so what we get is this effect on our capacitor. Alright, now this first one is going to be C1, and the second one is going to be C2. Okay, and because this is C1, this is also going to have a Q1. That's going to be Q1, this is going to be Q2. Alright, now, because this charge up here was created by the induction, by the sucking of charges away from this side, that it should stand to reason that our Q1 up here is equal to Q2 down here. And that is the case, that Q1 equals Q2 in our capacitors. So the charges across the capacitors are equal. Alright, so we can start doing some figuring here. Now, we know that as we go around a loop, our total voltage, as we go around this way, the total voltage has to equal 0. So if we're adding 12 here, we have to subtract a total 12 down here. So the total voltage across those guys is going to be another 12, or it's going to be a negative 12. Well, don't worry about the positive or negative. We're going to drop by 12 volts as we go across the two capacitors. So our delta V, as we go across the capacitors, is going to be V1, delta V1 plus delta V2, you know, our potential drop in the first one plus the potential drop in the second one. But we know that C, our capacitance, is our charge over our volume. Another way we can write that is our voltage equals charge over capacitance. Yeah. So we also know that, alright, so in this case our voltages here then are our delta V equals Q1 over C1 plus Q2 over C2, and this can continue. Okay, but since we also know that Q1 equals Q2, okay, and it also equals the total Q, and this whole thing equals the total Q over the total capacitance, then look what we get if we cancel all these Q's. We get 1 over our total capacitance equals 1 over C1 plus 1 over C2, and so on. Plus 1 over C to the n. Okay, and this, okay, this right here, this value is not, this is not the equivalent capacitance, but it is but it is the reciprocal of the equivalent capacitance. And so you add capacitors in series, one after the other, by 1 over capacitance plus 1 over the next capacitance plus 1 over the next capacitance, add them all together, and then find the reciprocal again, and that would be your total capacitance. Kind of like 1/2 plus 1/3 would equal 5/6, right? Well, the total capacitance would then be 6/5 if C1 equaled 2 and C2 equaled 3. All right, so if you have a capacitor that has 2 microfarads, and you have capacitor 2 is 3 microfarads, then you add them together. 1/2 plus 1/3 is going to equal 5/6, and then you flip it over, and this is going to be the total capacitance. Okay. Now, finally, we have capacitors with dielectrics, and this is going to be short and sweet. This is capacitors with dielectrics. Okay. So we have a circuit. And I'm going to put a pretty good space between our capacitance here. All right, and so what do we have here? We've got our capacitor. Now imagine that we have there's our positive charge, our negative charge accumulating on it. Okay, and there would be an electric field going across our capacitor. Now, imagine what would happen. Okay, in fact, how do we keep, in fact, this is one of the purposes for what's called a dielectric. A dielectric is essentially it's gunk. Okay, we need to keep the plates separate from each other. Otherwise, we have a short circuit and allows electron flow, and it fries the capacitor, and our electronics stop working, and we have to go buy a new iPod or whatever it is that we just short-circuited. Okay, so what we do is we use a dielectric, and a dielectric is really just gunk. It is non-conducting material that we put in there. And what dielectrics do is that they increase the capacitance. And so what a dielectric is really for is it's going to fit right in here. And I'm kind of leaving a little bit of space. But it fits in this region. Okay, and it's a device that fits in between the capacitor in order to keep them separated. You got to keep them separated. Da, 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 da. And because it increases the capacitance, it allows them to increase the maximum voltage. So purposes of a capacitor. So the purposes of a capacitor are to, purposes of dielectrics are to increase capacitance, dielectrics increase. They increase the capacitance, which means that they can increase the max voltage across that capacitor, and it keeps the plates from touching. Okay, so why does it increase our capacitance? Well, imagine we have a capacitance with no dielectric, and that would be, we'll call that C naught. It's too big. C naught is capacitance. So the C naught is the capacitance of your capacitor without a dielectric. Okay, and so the capacitance with the dielectric is given by, in fact, it's even smaller than that. It's like that. It's this constant. Okay, when we have a dielectric in there, we multiply our capacitance by this little value called, and this is kappa. This is lowercase kappa. Okay, and no sorority jokes here. My mother was a kappa, so don't go there. This is called, and this is the dielectric constant. Okay, and so here's what happens. If we put, let's see if I can explain this, because this is a little, all right. And so this has the loop, and we'll just imagine it's got the loop in there. And here are plus charges along this. Negative, negative, negative. Negative, negative, negative. Negative, negative. Okay. Okay. So, and in here we have our dielectric, and so we'll make a dielectric. It's gunk, and so it seems appropriate that it should be green. And so here's the dielectric. All right. And so on the atomic scale, which is really what we're, which is really what's happening here, is that there. Well, it doesn't look like there's a space when we normally do it, but on the atomic scale, there's a little bit of space. And what we do is we create some bound charges. And I'm going to do the best I can to explain this. We know that with our valence electrons, they're not locked in one particular place, that they are allowed to move freely about the atom. Well, what happens then is you get if you have this positive charge over here on this side, over on this side of the capacitor, you get electrons. Well, let's see if I can just do it. Here's your atom that's opposite any particular positive charge. Okay, they're right here. And they're going to have the electrons around them. So let's see if I can do this. Okay, and the electrons are going to want to move towards the positive charge more. And they create what's this is called a bound charge, and the negatives of the electrons want to hang out more towards the positive end of the dielectric. Okay, and that creates sort of a chain reaction within the dielectric, so that you have these other atoms going across, and this has the same effect, so that when you get over to this side, the electrons are on the other side of the atom, and so this tends to be a plus charge. Okay, when we get to the other side, and I wish I could make that better. I know that's going to look really, really small. So let's try that. Let's just select all of that and cut it. I'm going to make it really, really big here. So we have our our dielectric is only going to be a couple atoms thick, and so we're going to have our plus charges. We're going to have a couple plus charges over here. We're going to look at like just a cross section of our capacitor here, just so we can demonstrate what's going on. Okay, and here's our dielectric, and in the dielectric we have our dielectric here is only 2 atoms thick. But I want you to work with me here because the chain reaction is the same. Okay, so these guys make the gray circles represent the electrons reaching out, which makes these guys all have what's called a delta negative, which is a local negative charge around those atoms. And on this side over here, okay, these are all going to have a delta positive charge, which is attracted to the negative end of the capacitor. Okay, and so that's how this dielectric works. And it's not a conductor. You don't have electrons that actually flow through it, but you do get this shift of charge that moves over. But because they're not allowed to flow, they are called bound charges, and that's how you get the positives on one side and the negatives on the other. And that is capacitors with dielectrics. So this is one that you guys are really going to need to look at the book. Look at the chart of the constants for dielectrics that's in the book. And I realize this is a long lecture. Sorry, and it just takes a while to explain all of these. So I will see you guys on Tuesday. And your homework should already be up on Edmodo. If not, I'll make sure that it is. I'll see you tomorrow.